Let's make sure we're ready for this test on probability. We'll run through this practice test here just to make sure we familiarize ourselves and remind ourselves of all these ideas that we've covered. So again, just like normal, make sure you're showing your work for each problem and circle your answers. Let's see, a container contains 3 blue, 8 green, 2 orange, and 7 yellow marbles. Find the probability of each event. Write as a fraction in simplest form. So the probability of orange. Well, these are all equally likely, so we're going to do a theoretical probability in this case. First thing we need to do is we need to add all these up. So I notice that those add up to 10 and those add up to 10. So that means that there are 20 total. There are 20 total marbles here. So that means there are 20 different outcomes. So we're going to compare each one of these to 20, and we want the 2 orange ones. So there are 2 ways we can get an orange, so that's going to be the answer, but remember it said write it in simplest form, so we're going to reduce that to 1/10. And again, just to emphasize, we could write this as a percent, we could write it as a decimal, but we normally, because probabilities by their nature, they are long-term ratios. They're a ratio, they're a fraction. We're going to leave that one as a fraction, and we're going to do the same for almost all of these. Okay, so yellow or green, again, we're comparing that to 20. Yellow or green, so that means there are 8 of these and 7 of those, so that means there are 15 altogether. So we're going to reduce that to 3/4. So there's a 3/4 probability that we end up drawing a yellow one or a green one. Not blue, so anything but blue is okay. So you'll notice that there are 3 blue. If there are 20 altogether, that means there've got to be 17 that are the other ones. If you want to add those up, we do get 17. So this is going to be 17/20. And then purple. What's the probability of a purple? Well, let's take a look. We've got blue, we've got green, we've got orange, we've got yellow. There are no purple. So the probability of that would be, we can write it down the same way. There are 20 outcomes, none of them are purple. Or we could just flat write down the 0 and say, hey, we're done. The answer there, it's impossible to get a purple one given these conditions, and something that's impossible has a probability of 0. Okay, 5 through 8 have the same instructions. It says assign a probability of 0.5 or 1 to each one of these events. So let's just read through these and figure out what the answer is. You attend Sunset Middle School right now. Well, if you're taking this class from me, you attend Elkridge Middle School. So there's no chance of that. That's impossible that you attend Sunset Ridge. So that's going to be a 0. A coin toss comes up heads. Well, you toss a coin, it comes up heads. We know there are 2 outcomes. One of them is a head, so that's going to be a 1/2, or we're going to say 0.5. We'll go ahead and leave it in that format right there, just like they said as a decimal. The sun will rise in the east tomorrow. Okay, well, let's stop and think about that for just a second. Remember, we've talked about having some different background knowledge as we've gone through this probability unit, whether it's about cards or geography or different things like that. So in this case, the sun does rise in the east. The sun rises in the east, it sets in the west, and it's going to rise. 100% chance of that. So we're going to put a 1 there. And number 8 says you are a 7th grade student. Well, I teach all 7th graders, so this is going to be 100% right there. That's going to be a 1. All right, let's take a look at the next one, and the data in this one is kind of presented a little bit differently, and it gives us a little bit of a hint here. It says Lindsay drew candy from a bowl 40 times, so she did it 40 different times. Her results are recorded. So these are the different candies that she drew out, and this is the frequency or the number of times that she drew each one of those. So 7 peppermints, 8 butterscotch, 8 caramels, and so forth. Now, it's important to note that this doesn't mean that there are 7 peppermints in there, and it doesn't mean that there are 8 butterscotches in there. All this is how many times she drew one out. Maybe there's only 1 peppermint and she happened to draw it out several times. I mean, that wouldn't be very likely, but it's important to note this isn't how many there are, it's just the frequency of how often she drew that particular type of candy out. And she did 40 trials altogether. So I'm going to put the word trials right here because we use that terminology. Is this theoretical or experimental probability? Well, if you're going to do an experiment like this and all you're doing is saying the frequency that you drew each one of those out, this is definitely experimental. Okay, experimental. And there are some good reasons why we might do something like this, but let's compute the experimental probability of finding a butterscotch one. So this is going to be 8 out of the 40, and again, like up above, we're going to reduce this. So 4 goes, oh gosh, 8 goes into both of these. 8 goes in here once, and 8 goes in there 5 times, so this is 1/5. And then peppermint or caramel. Let's see, peppermint or caramel. So that's going to be 7 peppermint for the frequency there, and 15 caramel out of the 40. So that's going to be 22 out of 40. 2 goes into both of those, so that's going to be 11/20ths. So the experimental probability of drawing a peppermint or a caramel is going to be 11 out of 20. All right, let's take a look at the next one. There's a drawer with white, brown, and black socks. There is a 1/5 probability of randomly picking a white sock and a 5/8 chance of randomly picking a brown sock. Create a probability model for this situation. Well, what you'll notice here is they left something out here. So we've got white, which I'm going to do a W, brown, BR, and we could do BL, or these are short enough. I mean, gosh, on something like this, let's just write it out. So this is brown, and then this is black right here. Okay, and it says there's a 1/5 possibility or probability or chance or whatever word you want to use of randomly picking a white sock. So we're going to do 1/5, and then a 5/8 chance of picking a brown sock. So this is going to be 5/8. And then we don't know what this one is right here. So it says create a probability model. And remember, for a probability model, you have to have all the outcomes listed, and you have to have each one of their probability, and they have to obey the 2 rules for probability. So one of those rules is that they have to add up to 1. If we add all the probabilities up, it's got to equal 1. So let's do this. Let's get a common denominator on this. Let's use 40 for a common denominator. So I'd multiply that by 8. So I'm going to multiply this by 8. I'm going to multiply this by 5. So I'm going to multiply this by 5. So whatever this is, it better be something out of 40, and let's add those 2 together. So let's see, you've got 8 and 25, so that's going to be 33/40ths. So if you wanted that to equal 1, what would we have to add to that? Well, another way to say this would be, what would we have to add to this to make it equal 40? So that's going to be a 7, so that's going to be 7/40ths. Okay, so if this one's 1/5 and that one's 5/8, this one's got to be 7/40ths. And this can be a really useful thing, and we looked at this as we were going through and doing the unit of keeping them all with the same denominator. That can be really helpful sometimes. So if I'm going to circle these, I'm probably going to say 1/5, 5/8, and then I'm going to say 7/40ths, as ugly as this is. And what we've done here is we've listed each one of the outcomes and each one of the probabilities, so we've got everything set there. All right, let's take a look at number 12. It says, what is wrong with this probability model? More than one reason. Try to list as many as you can. Now, as long as you've got one, that's enough to say, hey, that's not a probability model. Okay, so we've got blonde, brown, and black, and then we've got a probability of 0.75, negative 0.25. So there's a problem right here. That is a negative probability. Okay, there's an issue. This one right here, that's 1.125, so there's a problem right here, bigger than 1. We can't have a probability bigger than 1, because remember, 1's 100%. You can't get any better than a sure thing, 100%. Okay, and then the other thing is if we were to add these together, let's see, 0.75 minus 0.25, that's 0.5. These add up to, so I'm going to say add up to more than 1. Add up to more than 1. Okay, so we've got 3 different reasons that we've pointed out here. Any one of those is enough to say, hey, that's not a proper probability model. We've listed all of them. You don't have to do all of them. Just get as many as you can there. Kind of impressive when you get more than one and get every single one of them. Okay. So let's take a look at number 13. It says use the tree diagram to answer. So we've got a tree diagram. Let's go ahead and fill out what we've got here. So this is going to be flipping a coin, and then either win or lose a game. So this is going to be head, head, win, head, head, lose. Follow this one, head, tail, win, head, tail, lose. And then we're down here, tail, head, win, tail, head, lose, tail, tail, win, and tail, tail, lose. It says list the sample space when flipping 2 coins and playing 1 game on the right side of the diagram. So we've got this done right here. Okay, there's our answer. Okay, that's our answer to this right here. We figured out what the sample space is. How many possible outcomes are there? Well, if you count those up, there are 8. And what is the probability of getting exactly 1 head and 1 win? Exactly 1 head and 1 win. Well, let's see. There are 2 heads and a win. That doesn't count, and that's a loss. 1 head and 1 win, so we've got that one taken care of. No win here. There's 1 head and 1 win. And there's nothing else with 1 head and 1 win. So the only ones that would work here are this one and this one. Those are the only 2 with a head and a win. 1 head and 1 win. So that's going to be 2 out of 8. So that's going to be 1/4. 1/4 would be our probability there. Okay, this last little bit, this is where we're, at least on this page, this is where we're using that fundamental counting principle, so hopefully we can buzz through this pretty quickly. It says determine how many outcomes there are for each situation, show your work. I really want to see your work. I don't just want you to write down an answer. So it says a basketball team playing in a 5-game tournament, win or lose, there aren't any ties. So they're going to play 5 games. So let's put our 5 choices out there, and they're going to win or lose. So 2 options there, 2 options here, 2 options here, and 2 options there. So we're going to multiply all those together, and when you multiply all those together, because that's what the fundamental counting principle says, you'd end up with 32 outcomes. Finished. And again, that would be a nightmare of a tree diagram to do. So good thing we've got that fundamental counting principle. We're going to roll 3 6-sided dice. So we're going to roll 3 dice, and then we're going to toss 4 coins. So 3 dice and then 4 coins. 1, 2, 3, 4. So for the dice, there are 6 outcomes for each one of those. For the coins, 2 here, 2 here, 2 here, and then we're going to multiply all those together. So this is a die, a die, a die, and this is a coin, a coin, a coin. When we multiply all those together, you can go ahead and do that on your calculator. You get 3,456. And again, the great part about that is you've got this gigantic number in your sample space, a huge number of outcomes there, but they were really easy to find because we could use the fundamental counting principle. Okay, let's do 18 and 19. Making a sandwich with chicken, ham, turkey, roast beef, or tuna. So we're kind of having a meat right here. So let's see, we've got 5 choices for that one. And then Swiss or cheddar. So we're choosing our cheese, and we either have Swiss or cheddar, so 2 choices there. And then mustard or mayonnaise, we're kind of choosing our topping. So we multiply those together, and we end up with 20. Pretty simple one, a pretty small answer here, even given that, I mean, look how short this problem was and look how big the answer was. So you can never tell just by looking. Okay, 19, picking from 5 theme parks and a 1-day, 3-day, or 7-day passes. So we've got to choose where we're going to go, and then we've got to choose the type of pass. So we've got to choose the park, and we've got to choose the pass. So let's see, we're picking from 5 theme parks. They gave us the number of theme parks we could choose from, and then we can either choose a 1-day, a 3-day, or a 7-day pass. So we need to choose a let's see, how many choices? There are 3 choices there. So when we multiply those together, there are 15 different outcomes in that sample space right there. 15 different combinations or possibilities there. All right, on number 20, we want to do a couple of things, and this does go back to tree diagrams. So it says draw a tree diagram and write the sample space. So here's what we've got. Tennis shoes or flip-flops. So we're going to do T or F for that. Jeans or khakis, so we'll do J or K for that, and then either a blue, a green, or a yellow shirt. Now, we want to make sure we've got enough space, so I'm going to do tennis shoes or flip-flops. So we're going to do a T here, and we're going to do an F there. Notice that I've got enough space here. And then off that, we're going to choose either, let's see, jeans or khakis. Jeans or khakis. And then we've got to choose a shirt. We've got to either choose one of 3 shirts. So this is going to be a blue, a green, or a yellow. Okay, so this is going to be blue, green, or yellow. Blue, green, or yellow. Same thing here, blue, green, yellow. And this one here, my diagram looks pretty ugly, but hopefully you get what's going on here. Blue, green, and yellow. All right, so that means this outcome right here is going to be tennis shoes, jeans, blue shirt, tennis shoes, jeans, green shirt, tennis shoes, jeans, yellow shirt. And then we're going to do this one. So this is going to be tennis shoes, khakis, and then we could do the blue shirt, tennis shoes, khakis, green shirt, tennis shoes, khakis, and yellow shirt. Okay, so that takes care of that. And notice that we've got 6 outcomes here. We had the tennis shoes and jeans with the 3 shirts, tennis shoes and khakis with the 3 shirts, and now we're coming down here and we're basically going to do the same thing, except for what's going to change is we're going to wear flip-flops. So flip-flops, jeans, blue shirt, flip-flops, jeans, green shirt. Whoops, I need that to look like a B. Flip-flops, jeans, yellow, flip-flops, khaki, blue, flip-flop, khaki, green, and flip-flop, khaki, and yellow. So we've got our tree diagram, we've got our sample space, so there's our sample space right here, so we want to make sure we do that. So that's kind of the work, and that's kind of the answer. How many outcomes are possible? Well, if you count up, there are 12. And it says show that your results match what you would expect using the fundamental counting principle. Remember, we're going to choose shoes, then we're going to choose pants, and then we're going to choose a shirt. And there are 2 options for two options for shoes, 2 options for pants, because it's either jeans or khakis, and then there are 3 options for shirts. So if we multiply those together, we end up with 12, and that matches up here, so we're in good shape there. And then it says assume choices are made at random, find the probability of wearing jeans and flip-flops. Jeans and flip-flops. Well, there are jeans up here, but no flip-flops. So jeans and flip-flops are right here. You'll notice that what doesn't matter is how many shirts we're wearing, or what color shirt we're wearing. So there are 3 out of the 12. So that ends up being a 1/4 probability. And then not a yellow shirt, not a yellow shirt. So you'll notice that those 2 are not yellow. Those 2 are not yellow, so we're up to 4. 6 and 8, so that means 8 out of the 12, so that's going to end up being a 2/3 probability of not wearing a yellow shirt. Now you might want to think about what's going on here, because if we're wearing jeans and flip-flops and we got 3 out of the 12, jeans and flip-flops, 3 out of the 12, well, it's just the 3 shirts that matter there. That's why that's a 3. And if we're not wearing a yellow shirt, that means we can wear anything else we want. That means we can use any combination of the blue and the green with any one of the other combinations of pants and shoes. So hopefully that kind of makes sense, but we've got 2/3 right there. Now on this next part, I want to look at this and then I'll show you what I've got written down below. So it says, after studying a unit on probability, Mr. Laws gave everyone in his class a fair spinner with 5 equal color sections. So they're all equally likely: red, orange, yellow, green, and blue. He asked 3 students to determine the probability that the spinner lands on each colors, and here's what the 3 students did. So Marcos did this. Marcos spun the spinner 30 times, and he kept track of his tallies, his frequencies, and then he computed his relative frequencies. So this one was out of the 30 spins, 11 out of 30. This was 4 out of 30, which reduced to 2/15, and then so forth for each one of these. Chandler did 3,000 spins. So he got 527 reds. He put that over 3,000, and he ended up with 0.1756 repeated, 622 orange. So that turns out to be, if you do 622 over 3,000, you get 0.2073 repeated, and then so forth for the other ones. And then Samantha wrote down this: red, orange, yellow, green, blue, and 1/5, 1/5, 1/5, 1/5. Now, here's the question. Whose answers would you trust the most, and why? So we've got Marcos that did 30 spins and then computed his relative frequency, or his experimental probability. Chandler that did 3,000 spins, 3,000 trials, and then computed an experimental probability. And then Samantha just wrote, well, these are theoretical probabilities. There are 5 different outcomes, each one's equally likely, so they're all equal to 1/5. So the question is, whose answers would you trust the most, and why? Well, let's take a look. I think this is the best answer. I would trust Samantha because it's a fair spinner. It's not a warp spinner. We have no reason to believe that it's not going to be equally likely. So each comes out equally likely. She did theoretical probability, which is more reliable in this situation. Now the other thing you'll notice is these numbers are kind of all over the place. They're not really like each other. But if you take a look at these numbers after 3,000 spins, all of these are pretty close to, think about what this would be as a decimal, they're all pretty close to 0.2. They're all pretty close to 1/5. And that's what's going to happen. A probability is a long-term average. It's a long-term ratio. So if he did 3,000 spins, we would expect these numbers to be really close to 0.2, and most of them are. One's a little over, a little under, a little over, a little over, and a little under. Okay? Now, next question. What would you say to each one of the students about their results? So I would probably say something like this. To Marcos, hey, if you're going to do experimental probabilities, you probably ought to do more than 30 spins. That's not really a long-term ratio that we can compute from that. For Chandler, we could say, hey, 30 trials, that's a pretty good experiment, but unless you're trying to confirm them, and doing 3,000 or 6,000, unless you're trying to kind of prove that the answers are 1/5, it's probably just better to go with theoretical. Now remember, there are cases where we have to do tons of trials. We gave you that example of the pass the pigs game, where you can't really know what those probabilities are without actually going through and doing a bunch of trials. And for Samantha, we'd probably just say, hey, great job. Theoretical probabilities are the way to go in this situation. They're a lot more reliable, and they're quicker for that matter. Now, let's go on to another problem that's related to that one. It says if the spinner was spun 480 times, how many would you expect to result in red? Well, if we're going to use the theoretical probabilities, the probability of getting a red is 1/5. So 1/5 of them, 1/5 of the 480 would be red. So we're going to do 1/5 times 480. I'll do implied multiplication there. So I'm going to grab a calculator and compute that answer right there. So we're going to do 1/5 times, so we'll turn this on. We'll do 1/5 times 480, and 480, and we end up with 96. So we would expect 96 of them to turn out to be red. Not blue. Anything but blue is okay. So if blue is 1/5, we'd add the other ones up. We end up with 4/5. So 4/5 of 480. So we do 4/5 times 480. Again, just do implied multiplication there. And what I'm going to do is I'm just going to go back up here and edit this. You can do the same thing on your calculator. I'm going to put a 4 here, multiply them together, and we're going to end up with 384. So if we did spin it 480 times, we would expect somewhere right around 384 of them to not be blue, and we would expect about 96 of them to be red. Now, that doesn't mean it's going to work out perfectly. Remember, theoretical probabilities are what we expect to happen, and experimental probabilities are actually going through the experiment and tallying things up. That's what actually happens. They don't always match up perfectly, but the more trials we do, the closer, we get. Now, on number 26, I do want you to be able to simulate a probability experiment. So on this one, let's just simulate this one. Again, on your calculator, you're going to grab this command, rand_i, and if we're spinning this spinner, we're going to do a 1,5. So rand_i and then a 1,5. That's on your calculator. Now, rather than set this up to show the split screen and all that sort of stuff, my calculator has that on it, and here's what we're going to do. I'm going to clear this off. I'm going to hit the math button. You'll notice you have to hit PRB, probability, and you'll notice this one right here in number 5. It says rand_int. That stands for random integer. So I'm going to do 1,5, and then I'm just going to keep track of these. Now, the first one is a 5, and I'm going to say that they are like this, that 1 is red, 2 is orange, 3 is green, 3 is yellow, 4 is green, and 5 is blue. So when this came up to be I'll make this a little bit smaller so we can see those. When this came up to be a 5 on my calculator, I'm going to tally a blue. Okay, so these are going to be the colors. This is going to be the tally or the frequency. Put a Q there. And then over here, this is going to be the probability. Okay, so I'm back. I've got the color, the tally, and the frequency and the probability. And this is what I ended up with. And this is kind of interesting. As I was going through it, I was getting a little scared. I didn't get any orange. I didn't get any twos for quite a while. And I was thinking, oh my gosh, I'm not going to get any of those. But here's how it worked out. I ended up with 3 and then 6 and 6 and 8 and 6. So if you'll notice when we compute that out of the 30 trials, 1, 2, 3 of them were exactly 1/5, and then there was a little bit of a disparity here. We had a few too many green and not quite enough red, but a pretty good probability experiment. And then if we were to go through, and the very last question here, it says, would you rely on your results? Why or why not? Okay, so we're going to say something like this: no, I wouldn't. Whoops, no, comma, I wouldn't. And think about the reason why you wouldn't. Okay, these are experimental, so we're going to say because this is experimental probability, experimental, and I only did 30 trials. Okay, so there's nothing wrong with doing experimental probability. I mean, most of the time we rely on theoretical probabilities, especially when things are equally likely. If we've got a good reason not to, or we want to do some verification or something like that, that's when we do experimental probabilities. But again, experimental probabilities become really reliable when we do lots and lots of trials. So doing 30 trials right here, we'd be kind of in Marcos's situation up here, where he only did 30, and yeah, he got kind of close, but not nearly as close as what Chandler did when he did 3,000 spins. So be my guest at doing 3,000 spins, but before you do that, I'd make sure that you understand, again, review the vocabulary that we talked about, go through this practice test a couple times, make sure you're familiar with the ideas. The test is going to be similar to this, but not exactly the same. So make sure, again, you understand the concepts more than just going through and memorizing, how to do a particular problem or something like that. You'll be in much better shape.